Welcome to today's forum session hosted by the Science Communication and Education Network, an action group of Blue Marble Space. Blue Marble is a global community and nonprofit research institute united by a shared commitment to understanding life as a universal phenomenon, inviting lifelong learners on a journey to explore space and advance a sustainable future. Today, our forum guest is Julianne Burns, a PhD candidate researching ice sheets and orbital cycles to seek clues about our Earth's future. I'll turn it over to her to present her work, and following that, we'll have an opportunity to have conversations with her about its implications, hopes, and possibly even actions for us to consider. So welcome, Julianne. We're looking forward to hearing your presentation.
Thank you so much. And thank you, Jennifer and Jim, for the opportunity to do this talk. That's really exciting for me. So thank you everyone also for being here. Today I'm going to talk about and hopefully discuss with some of you what I do for my PhD, how I got here, and where I see all of this going in the future. So for a bit of context and kind of aligned with the blurb that was probably sent out, I am a PhD student in New Zealand, although I'm currently in the US for a bit. And I study interactions of ice sheets and the atmosphere centered around Antarctica. So for me, it all started in New York, but not this New York, actually this New York, quite upstate where I grew up. And this is because the Adirondacks are one of the few places in the world that are still a geological mystery. They don't really know how they formed completely yet. So where I grew up was pretty rampant with geologists, and I found it very fascinating. And so from a very young age, I was obsessed with rocks and knew that I wanted to pretty much be a geologist. And that led me to going into the Adirondacks, exploring rock climbing and the geological features, becoming more and more interested in the earth science, specifically geology. After high school, I majored in geology and statistics at the University of Vermont, which is just in the northeast of the US. And I became quite involved in climate activism there because while I really loved the nature and everything where I grew up, I could already see really, really widespread changes in the climate just from kind of the 20 years of my lifespan and I guess the 5 or 6 generations of my family that go back there and the changes they would describe to me. So I became really interested in that as well. So after a few years at the University of Vermont, unfortunately decided that they were going to cancel their geology program. So I had to make a move for bigger and better rocks. And I knew based on people I had talked to, and although I had never left the US at that point in my life, I knew that New Zealand was really the place that you go if you really want to see the best rocks in the world. So I decided to go to the University of Otago, which is in southern New Zealand. It's right near an intersection of the Alpine Fault, which is a very large fault system in New Zealand. And there's volcanism. So I knew if I wanted to continue my studies, this would be a great place for me to go. And I was very lucky to be able to do so. So I continued my journey in New Zealand. I have kind of a fun throwback photo here for me of my first geology fieldwork notebook. I ended up doing over 100 hours of fieldwork in New Zealand, many of them independent, and I became a lot more comfortable in my field geology. But I still knew that throughout the fieldwork, I slowly became involved, met more people, and started hosting science communication workshops. I would highly recommend participating in the Climate Fresk, which is a 3-hour-long climate-focused kind of education workshop that I run in New Zealand, but they're run all over the world. And I did that alongside my studies. And then in New Zealand, eventually, after a few years, I moved on to doing my honors research. And for me, this is really the turning point. I met a great supervisor, Dr. Christian Oneiser, if anybody knows him. And he is a specialist in paleomagnetism, which is a really niche study. But oh my goodness, can you hear me?
Yeah, we can
Okay,
hear
it
you.
says I've disconnected if anyone can hear me. Okay, thank you. Apologies. Okay. So the study of paleomagnetism is essentially the study of Earth's magnetic field, which is quite niche, but it's kind of the tie point for studying past climates because you want to understand the age of all the data that you're looking at. So I was very lucky to meet Christian and to have him supervise my honors, in which I was walking around with a magnetometer. That's me far in the distance there. And essentially, with that, you're measuring the magnetic field around it, and you can study things such as kind of the type of rocks that might be below you and things like that. And this is kind of a key point of paleomagnetism. I slowly started exploring the different things that you can do in past climates, and that's what led me to my PhD, what I'm doing today. So through my honors at the University of Otago, I became involved in a project through IODP, which is the International Ocean Discovery Program. And this is kind of one of the main ways in the world in which people will join this program and go do Antarctic research. And basically, they run these big international collaborative trips down to Antarctica. And I was lucky enough to be involved in one of these by using a sediment core from them. So I was offered the PhD in Wellington, New Zealand, and I knew that I had to stay because I would not want to say no to an Antarctic PhD, as this was really kind of the cornerstone between the climate work that I like to do and the geology, and then also this adventure of being able to study such a remote location. So this really brings me to my PhD. So my PhD is focused on the specific IODP expedition, which is IODP 374, which was drilled in 2018. And it was led by my supervisor, Professor Rob Mackay, if anybody knows the names. But he went down in 2018 with a massive team. And on this boat, they would sail into the Ross Sea, which is right over here. And they took all of these sediment cores, which basically means they drop something down to the ocean floor and it drills down as far as it can go and pulls up sediment. And that sediment is a record of basically the past geology, the past sediments in the area. So specifically, this is the Ross Ice Shelf, which is part of Western Antarctica. And it's highly sensitive to climatic changes. So the goal of going and drilling down here was to hopefully get a record of past ice sheet movements as they would have gone over and back across the ice sheet. Specifically, the little one in the middle there, about a little more than halfway between the present day Ross Ice Shelf and the continental shelf. So, like I said, my PhD focuses on this course specifically, and the goal is really to capture the advance and the retreat of the Ross Ice Shelf, and then use the sediments to try to track how the climate has changed alongside those advance and retreats as well. And the ultimate goal of this really is to better understand how ice sheets react to past climates and how they might react in the future. So let's really get into kind of I guess, the nitty gritty of my PhD specifically. So we all know about the dinosaurs. So we can start there around the Jurassic. Land-based dinosaurs went extinct from an asteroid impact around 66 million years ago. And today, the remnant of that is this thin layer of iridium that's found all over the Earth. Here's a photo of me touching it in Italy, which might have been the best day of my life. So this is around 66. This is the KT boundary, if you see that up there at 65.5. So the Miocene, which is the time period that I study, the Miocene epoch, is all the way up here. So it is a long time ago, but it's really less than half of the time since the dinosaurs have been extinct. So the Miocene is really thought of as when the Earth started to look more or less recognizable to today. By the time the Miocene began, ice sheets in Antarctica were well established, but the northern hemisphere only had small land-based ice. This means that for studying the climate and ice interactions, it's actually relatively easy because there's less feedbacks with seasonal variations with the northern hemisphere happening. So here's one of my favorite graphs because it's actually quite simple to look at. But so the Miocene epoch started 23 million years ago. This specific time period that I'm looking at is between 17 and 14 million years ago, and it's called the Miocene climate optimum. And if you look at this graph here, this little hump around 16, that's the Miocene climate optimum. So in terms of recent records, and just this is atmospheric CO2 versus time down here. So we're all the way over here in the farthest right. And yeah, this Miocene climate optimum is this elevated area with this kind of light red line behind it. And we're looking at CO2 around 480 ppm. In present day, I have up in the right corner here the screenshot from today of what our atmospheric CO2 concentration is. And today we're looking at 431.5. So we're really not that far off from what we were seeing during the Miocene climate optimum. So this time period is really distinguishable because of the increased CO2 and temperature alongside a decrease in basically ice sheet volume that we're seeing. So when we think about warming, about increasing CO2 today, we usually think about anthropogenic climate change, so humans, industrialization, producing CO2 into the atmosphere. But back here, back in the Miocene, what happened was basically this thing called volcanic degassing. So a lot of volcanoes erupted, a lot of tectonic activity happened, and this released a lot of CO2. I guess the main difference is back then it was happening over a period of millions of years, whereas now it's happening over decades. So we have a similar template to look at, two time periods that are quite warm, so today in the Miocene, and then a big increase in CO2. So I'm thinking, how are the ice sheets reacting to this back then? And a lot of what we see is that it's not what you'd expect. It's not linear. And I will explain why. So my PhD is really about figuring out the relationship between the ice sheets, the atmosphere, the ocean, and then this thing called solar insolation, which is how much energy the Earth is receiving from the sun. And to understand that, we look to sediment cores, surprisingly. So these are the sediment cores that these are just examples of some that have been collected from underneath the ocean floor to try to study the past climate. So this on the top left corner, this is a photo of what they kind of just look like after they've been pulled out and then sliced. And the photo below it is actually a CT scan of these sediment cores. So similar to what you might do if you break a bone, we actually put these sediments into a CT scanner so that we can see the finest details. And we're looking for things like inclusions, fractures. There's countless of things. I actually have a bit of I don't think that'll load. But basically, I look specifically at these CT scans and I'm looking for something called ice rafted debris. And this is a big part of my PhD, is mapping out ice rafted debris inside sediment cores. Basically, if you see ice rafted debris, which will just look like little stones, you know that there's been ice sheet activity in the area. And by looking at this throughout the entire record, I can map out when there was and when there wasn't ice sheet activity. And then combined with essentially a billion other proxies, we call them, I can start to piece together a puzzle of what's happening with the ice sheets during this time. So this, I know, is a very complicated figure. It's from a paper I was part of in the beginning of my PhD with my supervisor, and this is the core that I'm working on. So essentially, we analyze these sediment cores and we get a million data points that need to be interpreted, and it ends up making quite a scary puzzle. And as you can see, the puzzle is quite messy. So there's a few things in the far I want to show you things that might look familiar. In the far right corner here, we have the CO2 parts per million and O18. Just think of O18 as a proxy, so as a signature of ice sheet volume. And CO2, I think we're all quite familiar with as something that can regulate warming on the planet. So a few examples of proxies or things I can extract from sediment cores to tell me new information are grain size. So I measure grain size in certain samples from the sediment cores to try to get things like current speed. I look at the different types of sediment to try to see ice proximity. So certain sediments will say that there is an ice sheet directly above, or that there wasn't an ice sheet until, maybe very far away, or we call distal. Foraminifera, which are kind of little cells, and those you can figure out things like temperature or ice volume. And then also magnetic properties, which is similar to what I talked about earlier with my honors research. We look at the magnetic signature all the way through the core, and we can actually get age from that because that lines up with the changes in the Earth's magnetic field, which we have really good records of, and many, many more. So this is really just to show that a lot of what I do is kind of constructing this massive puzzle. And for me, a reason that I really think I fell into this, or not even fell into it, chose this as a path, is because I love puzzles, essentially. And I get to go to work every day and decode these puzzles, which is really fun for me. Now, there's one more big component of my PhD that I haven't quite talked about yet. And I'm curious, once we get to the discussion, what everyone kind of knows about this and what they've learned about this in the past. But one thing I do want to discuss is how CO2 is affected in the atmosphere and how this shows up in the record. So here's my extremely accurate description of the Earth. So a few things here. As we all know, the Earth is essentially a sphere, and sunlight hits it unevenly, direct and intensely at the equator, and weak at the poles. So that imbalance is what drives our winds, our ocean currents, a lot of our weather, and the planet is constantly trying to even out that heat. So where I'm trying to go with this is that if we're getting constant CO2 input, maybe we'd expect the temperature to just constantly rise, but it doesn't. We get these things called feedbacks, and it's very complicated. And with my PhD, I'm trying to understand how these feedbacks have occurred in the past and how they might happen to potentially amplify the effects of climate change. So in terms of input, it's quite simple. We're just getting solar radiation, and this is actually over the Miocene. This is the record of insolation that we have. And as you can see, it's relatively quite a nice wiggle. However, this amount of input changes due to changes in the Earth's orbit, which happen over hundreds of thousands of years, which essentially makes the Earth at some points more prone to warming or cooling than others. And we actually see these cycles really clearly in sedimentary and even ice core data. And what this can tell us is a lot about how the Earth's orbit is what has caused ice sheet changes in the past. And I'm able to see in my data things like this. So this is the kind of the trademark paper on the topic, Variations in the Earth's Orbit, Pacemaker of the Ice Ages, which is from 1976. And it's talking about how, in the past, for hundreds of thousands of years, we've been able to trace all of the ice ages, and not all, but a large majority of kind of the climate changes that we're seeing to the Milankovitch cycle, so the changes in the Earth's orbit, and how just today in the present day, because of anthropogenic climate change, we're not able to do that anymore. We've fully gone off the scale. And this is kind of an example of what I'm looking at. So in the background here, we have O18 or ice volume, and we're looking at the different cycles of the Earth's orbit that it goes through. I know this is quite complicated, but I thought it would be fun to show some of the real data that people are working with. And I really recommend, if you're up for a bit of a challenge, one of my favorite papers here is the Barker 2025. It basically is a recent paper that discusses the distinct roles of Earth's changes in its orbit in the glacial cycles that we've seen more recently. So, yeah, if anyone's interested in that, I would absolutely love to discuss. That's pretty much a wrap on, I guess, what I do in as best of way as I think I can explain. But I would love to hear what everyone is curious about. What do you think about all of this? I know that it's tricky to, I think, explain the concept of complexity and the concept of feedback loops because it is complex. And a lot of my PhD is trying to figure out what we don't know and how much can we minimize the errors in what we don't know. So I ask if anybody has any questions or would like to discuss anything, please feel free to do so. Yeah.
Thank you for that wonderful presentation. I just want to get right off the bat and say you helped me realize how I really took for granted the magnitude of the puzzle of what you're really looking at and each of the pieces that it comes together. It's not just a 2D puzzle or a 3D puzzle. You're looking at 4D and more, if more exists.
Yeah.
And so thanks for
Thank
the
you.
research and for being able to present it to, a lay audience like me to kind of follow along with what you were presenting. So that was quite wonderful. I do have a whimsical question, though.
Yes, please.
As a future rock doctor, do you consider Earth to be one of your patients in light of what you presented today?
Oh, that is such a sweet question. I love that. No, I think Earth is really the doctor, to be honest. I think Earth will always come back and heal itself in a way. And I think humans are more the ones that should be worried. But we're more the patients in a way, if that makes sense. You know, the
Oh,
Earth,
that's
the Earth
lovely.
has all of the records for millions and millions of years. We're just trying to find them, go through the filing cabinets. But yeah, in a way, also, I think I hope that we really take on the responsibility of trying to help the planet in the next upcoming decades. Yeah. Thank you
Wonderful.
so much for your question, then. I see a question in the chat. Oh, yep. Okay. So Ronhan asks, he said he's interested in knowing more on what all things comprise the foraminifera. And do you also encounter ancient biological materials in the core? So yes, well, kind of, and yes. So I'm not a geochemist. I do mostly geophysics and geology. I do know a bit about foraminifera, though. They're incredible. I would absolutely recommend kind of Googling some images of them. They look very funky. Um, but essentially, what they can tell you is, I mean, my understanding of it is in certain foraminifera, so certain species will live more predominantly in different climates. So people do a very monotonous task of counting the foraminifera and saying like, oh, there's this many in this part of the sediment core that are this species. So we can sort of deduce more about the climate and things like temperature and from that. In terms of biological material, yes, we get plant matter and things like that, but I I don't typically deal with that myself. But I do. I guess one of the beauties of doing something like Antarctic research is that you always have these teams of hundreds of, like, I mean, maybe not hundreds, but 100 people, and there will be experts on this, and everybody works together on kind of their niche and puts it all together into a big puzzle. But yeah, I hope that answers your question.
Um,
Well,
Julianne,
go
I've
ahead.
got a couple of questions. The first one, how do you stop any of the contamination? You know, when you're bringing that sediment out and you're testing the various things, whether
Yeah,
that's sort of testing CO2 content or even the biomaterial that you talked about. So how do you make sure it's clean?
yeah. I mean, some of the hmm, everything is kept quite like sterilely. I'm trying to think. When we get the sediment cores, I mean, for what I'm looking for specifically, contamination isn't very important. So I can just speak
Right.
on what I use essentially. So for things like grain size, for example, you're kind of, yeah, I guess contamination isn't really a factor in what I do, which is lucky for me because it eliminates a lot of work there. But
Yeah.
we're eliminating anything that would be kind of like dust that could possibly get in it, and everything is kept completely sealed until we're ready to use it. So it'd be pretty impossible for anything to contaminate, and if it did, we would see the signal in the data quite obviously. Yeah.
And secondly, because I bring a group of students down to Vic Uni every couple of years, and we have sort of various talks. And James Crampton sort of has hosted before,
Oh, he's
and
amazing.
James has talked about the Mars orbit also influencing evolution on Earth. And so,
Yeah.
you talked about the Milankovitch cycles and obviously the orbit of the Earth. Do you look at the other planets and their potential impact?
Yeah. So the Milankovitch cycles are essentially just the interactions of Earth with the gravities of other planets. So there's basically pretty much everyone that I know that studies anything with Milankovitch goes off of this one paper where some mathematician from France, I think, has outlined the orbital cycles of Earth back 50 million years. And this is just a very complex set of equations that takes into account where the other planets were at the time. So we're looking at like all of the planets and all of their gravitational fields and how that's pulling or impacting Earth's orbit. So I guess Mars must be, I don't actually know which Milankovitch cycle is which planets, but I know it does take into account all of these. Yeah.
Yeah.
That's quite cool
Well,
though. I'll ask James about that.
yeah. No, he's a fascinating man.
Yeah, yes. Yeah. Cool. Thank you.
And I'll jump in then. Could you tell me a little bit more about the climate fresque that you run?
Yes. Oh, I would love to. Um, I Climate Fresque is a French nonprofit organization that runs like these 3-hour workshops where you play a card game and run through going from kind of human human things such as industrialization, agriculture, all of that, transportation, all the way to things like social inequality and famine. And you run through how the components of the climate system and the humans' impact on that can lead to things like that. And then you have a like an hour and a half discussion on sort of what you can do in your community to actually help this. And it's really great. I've run it for some classes at Vic Uni, run it in the public. I've run it for IPCC scientists, which is really cool. So I've done a big, yeah, I'd be happy to run one when I'm back in New Zealand for your class if they're ever down.
Yeah, well, we'll be coming down again next year, so that sounds
Okay,
amazing.
we'll keep in touch. They're really great, and I'd recommend for anyone else who's listening to look into it. It's actually it's not that popular in New Zealand, but globally it's really taken a hold, which is great.
Yeah.
Yeah. Yeah.
So,
Yeah. Thank you.
And was that the climatefresk.org? Do you happen to know
I'll
with
send a
web
link into
search?
the
Okay. Yeah,
into the chat.
please.
Yeah, it's really wonderful. I think every time I end up talking to people, this becomes my go-to because it's just such a great organization. Here we go. Okay, there it is in the group chat
Thank you.
now.
and so it
Thanks.
sounds like it's for all ages then. So from school age kids all the way up to sort of, if you do an IPCC, then that'll be James Rennick and that at the uni.
Yeah. Yeah, they have a special one. They don't recommend it for people under, I think, 10, just because some of
Right.
the concepts can be a bit difficult to grasp. But it goes, I think there's a juniors version from 10 to 14. And then above
Okay.
that, there's the adult version. And then it's 14 to however you want to do it.
Yeah.
Yeah.
Can I actually go back to asking about the iridium band? So Have you touched it anywhere else other than Italy? And when you
Yeah,
approached it,
yeah.
did you recognize it right away? You're like, wow, there it is.
I was super lucky. I was on, I mean, perks of doing a PhD, honestly. I was on like a summer research school in Italy, which I feel so grateful to have gotten. And so they took us there. Um, it's really cool. This iridium band is present all around the world. And it's basically they just know that this is from the meteorite because iridium is so dense that all of it that was naturally on Earth has sunk to the core. So when geologists found this, they were like, what is this doing here? And then they realized it traced all around the globe. So it's very cool. I did touch it. It was, felt a bit of a spark. It was phenomenal.
Because there's the KT boundary not far from you as well in the wider Lapper.
Yes, yeah, I haven't touched it there. Maybe that'll be my life mission.
Yeah, cool
Touch
little
all around the
photo at each
globe.
place.
Yeah, that'd be quite cool, wouldn't it? Yeah. Yeah, but that's very cool. I think it's great to see, I guess with geology, it's such a hands-on science.
Mm.
It's there's millions of ways to actually physically see it, which is can be really good for people. Yeah. Oh,
So
cool. He was able to touch it in Spain. Oh, that's awesome. I'm going to Spain in a few months. I will try to find it, add it to my collection. Thank you. That's so great.
so you think
Yeah.
pattern, because you mentioned pattern seeking a couple of times, you think that's quite an important skill?
Sorry, what was the word you said?
So you mentioned you sort
Ah,
of look at the data and try to find those
totally.
patterns, and then obviously geologists, it's very important. And so, is that something you
Mhm.
were sort of just naturally born with, or you worked on, or
I mean, I think since I was a very little kid, I just love puzzles, like word puzzles, Sudoku, all those things. And I think people that are naturally really drawn to kind of looking for patterns and things find a real home in geology because, you're really just matching up these huge, huge puzzles. And yeah, there's a whole kind of branch of what I do that literally is kind of pattern seeking and people call it wiggle matching, which is when you're looking at data and you're trying to match up all of the wiggles that you're seeing and seeing if you can see anywhere where they all go up at the same time and go down. And that's kind of the basis of how a lot of this starts. Is you're like,
yeah,
this pattern looks very familiar. Is this actually related to this? And then science is born. Yeah.
cool.
Never thought I'd have a forum with the phrase wiggle matching.
Wiggle matching. Yeah, it's a term.
Well,
Thought
Jennifer,
of
you
that.
should watch the Wiggles from Australia with your daughter.
That's exactly what I do.
But yeah, very very famous kids TV program down here.
Hmm.
Do we have any more questions from our participants today, our live participants? While we wait for possibly any more to come in, coming from a high school teaching background, and I think Jim kind of touched upon this when he was asking about the pattern skill. What advice might you have for high schoolers who are maybe developing an interest in rocks or geology or anything of the like? What would you suggest them to hone in on, or what would you
Mm.
suggest that they nurture?
Yeah, that's a great question. I actually think about that quite a bit, to be honest, because I think geology it's a really interesting discipline in that it combines every single science and topic you could possibly imagine. Like I do my PhD on the same project alongside someone else who has just like a pure chemistry background. Um, I was not great at chemistry in school personally. I was much more on the physics side of things. But then also a huge part of this is actually kind of people that are really good at like English and learning how to actually translate what we're seeing into words is such an underrated skill. Um, I guess for me, I was very lucky in that I was able to say I'm passionate about this and I want to pursue this for an education. I know not everyone, I guess, has that sort of privilege. So for me, I'd say if you can and you're passionate about something, just obviously go for it and talk to your teachers, talk to, when I was in high school, I was actually like cold emailing people that were geology PhD students saying, what did you do in college? What did you study? How did you get into this? I can go back to 2016 and I find some very embarrassing emails to people saying, you're my hero. How did you get into this? But those actually were really inspiring for me. And I would recommend people to do the same, because now that I've gotten like some emails kind of like that now, I find it so endearing, and I'm so excited for those people to hopefully continue with that. And I guess everybody's there to help you. Everybody in geology loves geology and wants more people in geology. So absolutely come join the big family.
Great.
Yeah.
Thank you for
Very
those
cool.
inspirational words. Now, coming from a different perspective, you mentioned some of the data and the ice cores and so on. Do you happen, and I don't know if this is within your expertise or your contributions, but then do those data get deposited in any kind of repositories for later reuse by people who might be interested? And might you be able to talk at all on those?
Yeah, so like data repositories for
Yeah,
um yeah,
not the
everything is
Wiggles data, or
completely
yeah.
open public. Everything, like, I can't speak for other kind of disciplines, but I know in paleoclimate everything is so well archived and public access. So there is Pangea, which is a really, I guess, kind of a popular data repository. All of the sediment cores are stored in these very large facilities. There's one in Germany, one in Texas, I think one in Korea. And so from all these expeditions, all the cores are saved and everything goes there. And I'm not sure what kind of the year period is, but after a certain number of years, all the data becomes public. So there's a big push right now in the field to, I guess, instead of going and collecting more cores, to do more analysis on the ones that they already have. So a few projects are being funded that way, which is really cool.
Great. That sharing was wonderful to hear. You have
Yeah,
a
it's
question
so
in the chat?
interesting.
Oh, sorry.
Oh, sorry. No, it's okay.
Sorry.
Oh, Alex
I
is
got
asking.
excited. Yeah, you got a
Yeah.
question in the chat. So go ahead and read it and respond.
Oh, you're a space science student at VUW. That's awesome. If you ever looked at weather geology interactions on other planetary bodies in the solar system, you are totally, yes, I love this concept. In terms of weather and geology, I'm I guess I would think of a broader term for the word weather, if that makes sense. But I have thought a lot about the concept of, I guess, paleoclimate on other planets and kind of the geological scars that leaves. I'm personally really interested in, um, I guess, places like, I'm not sure if you're aware of like Europa, so some of the moons, and I'm really interested on about how you can sort of use geology in a broader sense to compare some of the surface patterns that you see on different planets to ones you see on Earth, and see if you can interpret anything about, I guess, sort of the climate or the weather, or just sort of the things that are causing that surface to occur. There's the Earth is the best analog that we have for other planets. So that's a really cool sort of budding field of research that I'm also very excited about. Basically, planetary geology. Yeah, if that answers your question. In terms of weather and geology, I'm not sure, but yeah, cool.
Thank you, Alex, for
Great
asking that
question.
question.
Yeah, thank you everyone for your questions. It's so great to hear.
And now I'd like to actually ask you a closing question, which has been the question of the month. If you could send
Oh,
a
okay.
message, if you could send a
Well, thank you,
message
Clive.
1,000 years from now and it would be read and understood, what would that message say?
Oh gosh, 1,000 years, and it would be understood.
It would be understood. And maybe what the guy asked us to everyone else, but then to a geologist, maybe the time scale's a little bit different. But 1,000 years,
Yeah,
we'll stick with it.
1,000 years is very soon. Very soon. Oh my goodness. Oh, I think it depends so much on if yeah. Oh gosh, you stumped me. What would I say? I think my initial thought is to kind of say maybe to the geologists of 1,000 years from now, I'd say, I promise we were really trying. Like we were really trying to figure it out. And I'm not sure if by then, a big thing for me is because I work in the Antarctic Research Center, is a lot of what we see is very doom and gloom. Or like it's quite stressful about the state of our future planet. So I guess my message to in 1,000 years would be: I really hope we did enough and we were really trying, and let me know how it turned out. That's all I can say. That's such a good question, though. It's something I'll be thinking about, I think, for a few hours after this.
It's a cool answer as well, then.
Yeah, for a few thousand years. Yeah.
Well, thank you very much. And to our live audience who joined us today, thank you. And for all those who will be viewing in the future, we hope you had a wonderful time, gleaned something new, or got new questions to think about. So thank you all very much and have a wonderful day.
Thank you so much, everybody.